Good morning, everyone. I'm David Kruckemyer from Ventana Microsystems. My co-author today is Elad from Blue Cheetah Design. You've heard from him earlier this morning. We're here today to introduce a lightweight transaction and link layer specification for die disaggregation applications utilizing the BoW interface. So here's a quick look at the agenda. I know we're running a little bit behind. There's a lot to go through. I'll try to make it quick. I'm going to start with the goals for the design goals for the specification and show how those goals relate to die disaggregation. I'll go into the die-to-die interface architecture, discussing the transaction layer and its functions. One important thing that I'll introduce is the concept of interface profiles. These enable implementation flexibility and interoperability between designs based on this architecture. After that, we'll go into the link layer and talk about its services, such as error correction and link training. And then I'll talk a little bit about virtual wires, which allow or minimize the number of interfaces or signals that go across the interfaces between chiplets. So to start with, our primary goal was to develop a simple low-latency die-to-die interface with bandwidth scalability, technology portability, and feature extensibility in mind. We started with BoW as a foundation, and we were concentrated on die disaggregation applications rather than package aggregation, and optimized around a relatively quiet electrical environment within a package. One example optimization is the selection of ECC for error correction rather than CRC and retry. ECC avoids the complexity of CRC retry handshakes, the latency of CRC computation, and the area overhead of retry buffers. The link layer also accommodates different numbers of BoW slices and data rates to provide bandwidth scalability and supports different serialization ratios on opposite sides of the link to enable implementation flexibility. In particular, the two chiplets on a link can be implemented in different process nodes, and as long as the data rates are matched, the link layer logic in each can be operated at different serialization ratios and therefore different frequencies. Finally, the specification defines a modular framework that enables extensibility, and both customization and interoperability can easily be achieved. So what is die disaggregation? A few people have talked about this earlier. Basically, we start with a monolithic SoC, or a complete system design, and partition the functionality into chiplets based on scalability, differentiation, reuse, or any other desirable system property. To support this design style, we wanted to enable arbitrary cuts on the on-die interconnect without introducing any latency or complexity. In particular, die disaggregation should be transparent to system IPs, so our die-to-die solution utilizes standard system interfaces that make the IPs seem like they're talking directly to each other. As many of you know, one challenge is that there's no such thing as a standard interface for on-die interconnect. And SoC designers are used to having the flexibility to optimize their interconnects to accommodate the diversity of system IPs. To provide this flexibility, the specification introduces the notion of interface profiles, which I'll describe in detail later. So the starting point for a die-to-die interface is really a bunch of on-chip wires. And the die-to-die architecture was designed to maintain that abstraction as much as possible from both a latency and complexity perspective to minimize the cost of die disaggregation. So the architecture for our die-to-die interface consists of a number of conceptual layers, including a transaction layer, a link layer, and a physical layer. Each of those layers serves a particular purpose. This diagram shows how the layers are related in the transmit or TX interface on chiplet 1, you see on the left there, and the receive or RX interface in chiplet 2, where both chiplets are connected by one or more BoW slices. On the transmit side in chiplet 1, information flows from the on-die interconnect at the top to the transaction layer, through the link layer, and down to the physical layer. And then on chiplet 2, the information flows from the physical layer up through the link layer, up to the transaction layer to the on-die interconnect at the top. A die-to-die link consists of two of these flows, one in each direction between chiplets 1 and 2. I'll describe the transaction layers and link layers in more detail, but I'll leave the physical layer description to the BoW specification. The primary function of the transaction layer is to translate between protocol transfers or packets on the system interface, which is the interface with the on-die interconnect, and the transaction layer translate those into and from transaction layer packets or TLPs on the link layer interface. A system interface implements one or more industry standard protocols, such as AXI or CHI, that can be comprised of one or more channels. A protocol transfer in this context is simply the transfer of information on one of those channels over one or multiple cycles. From a system perspective, the TX transaction layer acts as a responder, or a subordinate, as you might know in ANAXI, to the on-die interconnect on one chiplet, while the RX transaction layer acts as a manager or a requester to the on-die interconnect on the opposite chiplet. The transaction layer also implements any protocol-defined flow control, such as value-ready signals in AXI or link credits in CHI. As a result, integrating the die-to-die interface is as simple as integrating as any standard bus component. Lastly, the transaction layer assigns each TLP to a specific TLP stream, and the TX and RX transaction layers implement a credit-based flow control mechanism internal to the die-to-die interface to manage the flow of information on each channel independently. So I'll show a little bit more about transaction layer packets here. This diagram illustrates how information is transformed and encapsulated at various points in the die-to-die interface. At the top, protocol layer packets are formed by concatenating the information received on the protocol channel. To create a TLP, a 12-bit header is added to the protocol packet, which then becomes the TLP payload. This header consists of an aux field and a type field. The type field, of course, identifies the type of the TLP, while the aux field carries auxiliary information such as flow control or status based on the type. And so, yeah, an important example here is that the type actually identifies whether it's an AXI AR packet or a CHI rec packet, for example. TLP encapsulation occurs for each TLP stream individually, as represented by the dashed box. TLP streams are grouped into TLP classes that basically correspond to an interface protocol. For example, a TLP class for AXI consists of all the TLP streams that correspond to the individual AXI channels. System interfaces may implement one or more TLP streams. This classification allows implementations to optimize the metadata for a given TLP class and is particularly relevant for the flow control mechanisms I'll discuss shortly. The way protocol information is aggregated into TLPs is specified by an interface profile. Interface profiles are the means to support interoperability between the die-to-die interface implementations. Specifically, if two die-to-die interfaces on a link implement the same interface profile, they can communicate with each other. The transaction and link layer specification describes what an interface profile must standardize for interoperability. For example, an interface profile defines the supported interface, the interface protocols, the inclusion or exclusion of optional signals for each protocol, the width of each signal on the system interface, and other items there. The link layer working group has published a number of profiles for Ventana chiplets as well as generic CHI and AXI profiles, and members are currently defining additional profiles. Furthermore, the specification framework allows anyone to develop their own public or proprietary interface profiles, enabling designers to create custom ecosystems of chiplets that leverage the underlying link layer architecture and existing physical layer implementations. The transaction layer is responsible for controlling the flow of TLPs in each stream using a credit-based mechanism. Each TLP stream has its own pool of credits, where one credit corresponds to a TLP buffer in the RX interface on the opposite side of the link. As expected, a credit is consumed when a TLP is transmitted, and a credit is granted when the RX interface removes the TLP from the buffer. These pools are independent, of course, ensuring that streams are non-blocking with respect to each other. The RX interface grants credits using two methods. When link utilization is high, the aux field in the TLP header can transfer a small number of TLP credits, effectively reserving a small amount of bandwidth in the link for flow control. On the other hand, when link utilization is low or more credits are required, there's a credit TLP, excuse me. There's a credit TLP that is defined by the specification that allows the link layer or the transaction layer to transfer the maximum number of credits per stream. In this case, the latency is reduced because the TXC interface is always guaranteed with credit to be supplied with credits. To select between the two methods, the transaction layer utilizes a greedy algorithm that transfers the maximum number of credits possible. An interface profile may also define additional credit TLPs that are specific to a TLP class in order to optimize the transfer of credits based on the transaction structure of the protocol. Now I'll provide a brief introduction to the link layer and its functions. Primarily, the link layer ensures the reliable delivery of TLPs using an error-correcting code. It frames multiple TLP streams into a single bit stream comprised of link layer packets, or LLPs, and it manages the interfaces with one or more BoW slices, each of which operates independently. In addition, with the assistance of the PHY, the link layer performs training on the link, aligning the phase within a slice, as well as the skew across slices. These next few slides will go into these functions in a bit more detail. Returning to the previous illustration, we can see how the link layer transforms information between the transaction layer and the physical layer. The interface with the transaction layer transfers one or more TLPs as determined by the number of TLP streams. For each stream, the TX link layer applies sected ECC with a small code word for protecting the header and a portion of the payload, and a large code word for protecting the remainder of the payload. Once the check bits are added, the TLP is padded with zeros and quantized to 32-bit granules. The choice of granule size is a trade-off between implementation complexity in terms of muxing and demuxing and transfer efficiency. And 32-bit granules strike a good balance between the two. Once a TLP has been quantized, the TX link layer selects from the TLPs that have credits available and packs the TLP granules into 512-bit LLPs. An LLP consists of a 32-bit header and up to 480 bits of 480 bits and 15 granules of payload. The TLP header is also, the LLP header is also protected by its own code word, but it provides framing information identifying the location of the TLP headers in the LLP. After the LLP has been packed, it is divided into fragments that are assigned to various slice logic interfaces on the PHY. And the group of fragments transferred on the interface with the physical layer is also known as a bundle. This process is effectively reversed in the RX layer, and bundles received on the interface with the physical layer are transformed into TLPs presented on the interface with a transaction layer. So as I mentioned in the previous slide, the link layer employs two different sected codes for error detection and correction. There's a small code word or header code word that is applied to the headers of the TLPs and the LLPs and consists of 26 data bits and 6 check bits. Large code words or payload code words are applied to the remainder of a payload, a TLP payload, and consist of 120 data bits and 8 check bits. Notably, small code words correspond to single granules, which are guaranteed to be received atomically in a single bundle. Large code words, on the other hand, may span multiple bundles and hence may be received in multiple cycles. This property of small code words implies that the framing information encoded in the LLP and TLP headers can quickly be decoded and corrected in line, minimizing the latency in the RX interface. However, large code words do have better data transfer efficiency, making them suitable for large payload, making them suitable for the payload in larger TLPs. The size of the large code word is determined by maximizing the protection against errors while minimizing the efficiency loss. We found that because of TLP quantization, longer code words did not provide more efficiency gains, but they did offer less protection. On that note, and this is important, this scheme has provided to be extremely robust. Assuming a raw bit error rate of 10 to the minus 15, and assuming a link consisting of 8 slices operating at 16 gigabits per second for a total of 2 terabits per second, the probability of an uncorrected error in 1 billion hours is less than 0.1%. So we believe that ECC is an adequate error detection and correction mechanism for in-package die-to-die interfaces while providing advantages, as we discussed earlier, over other possible schemes. An additional responsibility of the link layer is link training. In the current specification, the link layer assumes that the physical layer performs lane alignment so that the timing relationships between the clock and data lanes meet the BoW constraints. The remaining alignment issues result from serialization and deserialization of fragments and from differences in timing within a bundle. The link layer corrects both by transmitting a known pattern on the TX interface and by adjusting the received pattern in the RX interface. The group of the diagrams on the left assumes a single slice with a 64-bit fragment and illustrates the potential phase alignment errors within a slice. On the left, the TX interface transmits granules 0 and 1 in the same cycle, but if the serialization state in the TX doesn't match the serialization state in the RX interface may place the granules in the wrong place at the wrong time, as shown in the middle. To correct this error, the link layer adjusts the deserialization state in the RX interface based on the received patterns so that the granules both arrive in the same cycle as shown in the right. This is RX good and RX bad. The group of diagrams on the right assumes two slices, also with 64-bit fragments, and illustrates the potential skew alignment errors between slices. The two slices operate independently and have no timing relationships with respect to each other. In this case, the TX interface illustrated on the left transmits granules 0 to 3 in the first bundle. Oh, sure, yeah. So I'll hurry up here. So the TX interface transmits one bundle in the first cycle and a second bundle in the second cycle. And you'll see that due to differences in timing in the middle diagram, that the fragments on one slice may be received at a different time than the fragments on the other. To correct for these differences, the link layer specification defines a D-skew buffer that aligns the received fragments into a common clock domain. The RX link layer then adjusts the delays in each fragment to account for any fixed skew, as well as any variable skew that may occur due to changing operating conditions, aligning the fragments in the bundle as shown on the right. Finally, to simplify the physical interfaces between chiplets, the transaction and link layer specification also defines virtual wire functionality. Virtual wires allow the transitions of physical wires to be transmitted from one chiplet to another using the die-to-die interface. These signals must have level-sensitive semantics, and examples are device interrupts or status signals. However, by using multiple virtual wires, more sophisticated signaling semantics, such as handshakes between the chiplets, can be realized. Virtual wires only require link bandwidth when a transition occurs. When an input wire on the TX interface transitions, a virtual wire TLP is transmitted, signaling the new level of the wire. When a virtual wire TLP, one more slide. When a virtual wire, or this is actually the last content slide. So when a virtual wire TLP is received, the RX interface, of course, transitions to the corresponding output wire based on the received signal. This combination of events propagates the signal state from one chiplet to another. In the current specification, up to 1,024 wires are supported, and to ensure interoperability, an interface profile will specify the number of virtual wires as well as the definition for those wires. So, as I promised, we're wrapping up. Today we've introduced a lightweight transaction and link layer specification for BoW interfaces that is simple and has low latency. The framework we described is scalable, portable, and extensible, making it suitable for a wide variety of die disaggregation applications. Finally, interoperability and customization are achieved through the definition of standard and custom interface profiles, allowing system designers to optimize their die-to-die interface implementations to meet specific system requirements. Thank you for listening. Also, this is how you want to, if you want to get involved, you can see how much the link layer group has accomplished so far. And if this topic interests you, you can join our meetings on Thursdays at 9 a.m. Pacific. The working group, as I mentioned, is publishing additional interface profiles and currently developing a sideband communication interface for interface initialization and management. And lastly, you can find all of the current specs in development on the ODSA GitHub repo. Thank you very much.